This is the first video on section 7.7, triple integrals. And I'm going to talk about definition 228. I obviously have not written it out in all of its gory detail on the board here. You have that in your notes in front of you so you can study that. But here's basically the idea. When you learn to integrate in Calculus 1 and Calculus 2, you're integrating over a line segment. So you took a line segment and you chopped it up into a bunch of little line segments. You took a representation point out of your little line segment, calculated the function value, multiplied by the length of the line segment. Recently, we learned to integrate over R2. So you took a rectangle, chopped it up into a bunch of little rectangles, picked a representative point out of that rectangle, calculated the function value, multiplied by the area of the rectangle. Here in R3, well, guess what we do? We integrate over a box. So we take our box, we chop it up into a bunch of little boxes, pick a representative point out of that box, calculate its function value, multiply by the volume of the box. And then we take the limit as, well, the number of boxes goes to infinity, the volumes of the boxes go to 0. And so that's what we do, and that's how we get an integral in R3. But just like in R2, we have something called Fubini's theorem. And in R2, that said if you had a rectangle, you could just integrate over each of these intervals. And basically what that meant is you regarded the other variable as a constant. You took an antiderivative with respect to one variable, treating the other as a constant. Well, we have a Fubini's theorem for R3. If you're integrating over this box, this rectangular prism, then that's what R is. And then we can say, all right, we're going to integrate over the x interval, the y interval, and the z interval. And we'll just have a triple integral. We'll calculate the antiderivative here. And so we'll look at the integral with respect to x, then the integral with respect to y, and then with respect to z. We work from the inside out, just like we do with functions of two variables. That's what Fubini's theorem says. And so in the next video, we'll look at an example where we just integrate over a rectangular prism. I forgot to mention one other thing. Okay, so when you look at Fubini's theorem in the notes, there were 6 different ways to write this, right? And so we can integrate in any order. And that's because when we have 3 intervals, there are 3 factorial, which equals 6 different ways to arrange these intervals in order. So we can integrate with respect to x first, then y, then z, or we can switch the order of that. Okay, so we could integrate with respect to, say, y, then x, then z. And so there are 6 different ways to do that. That is written in your notes. I did not write all 6 on the board. And so the idea is also in R2, when we have a Fubini's theorem in R2, we said, okay, both integrals were correct, but it might be that both integrals aren't equally easy to calculate. And so the order doesn't matter as far as getting the correct answer, but the order might matter as far as the ease of working the problem. And the same thing happens here, okay? So the order doesn't matter as far as Fubini's theorem is concerned, but the order might matter as far as you're concerned as you're integrating these, because some orders will be easier than others.